Section 3 introduces an application that we'll look at quite a bit in chapters 3 and 4. It's the damped spring problem. Let's imagine you have a spring that's attached to the ceiling and has a weight on the bottom, and the mass of the weight times the acceleration, let's say y of t, is the height of the mass that's attached to the spring, where y equals 0 is the equilibrium position. So y is positive if the mass is above the equilibrium position, negative below. Then Newton's second law says the mass of that weight times its acceleration is equal to the forces. Well, there are two forces acting on it. One is the force of the spring itself, which is proportional to the displacement from equilibrium and in the opposite direction. So it's minus ky. If y is positive, the mass is above equilibrium, the force is downward. If the mass is below the equilibrium point, the force is upward. It's in the opposite direction. And then there's another force, a damping force, due to, well, they give the example of a shock absorber with a liquid around it. But maybe it's the damping of the spring itself. But anyway, we're assuming that there's something that's damping the motion, and that's a second force, which is proportional not to the displacement but to the velocity, and in the opposite direction. In other words, if the weight is going upwards, the force, that dy dt is positive, the force is downward. If the weight is going downward, dy dt is negative, the force is upward. It doesn't matter whether y is positive or negative, it's the derivative of y the force is proportional to in the opposite direction. So we have mass times acceleration, which is second derivative of position, is equal to the force of the spring, which is proportional to the displacement from equilibrium in the opposite direction, and the force of the viscosity, the friction, which is proportional to the velocity and in the opposite direction. So you take everything on one side and you have a constant coefficient second order linear homogeneous equation. And we've been dealing with first order equations in chapter 1, and then chapter 2, systems of first order equations. This is actually a single second order equation. You can reduce it to a system of two first order equations, and they do that here, but most of the time we're not going to do that. We're just going to deal with it, at least in this section, as a second order problem. So how do you solve this? This section is a little different from the rest of the chapter, since we're just looking at a second order equation. How do you solve it? For example, let's suppose b is 3 and k is 2. Then this is your differential equation. Well, they say just to guess a solution, try a solution of the form e to the some constant times t, e to the st, e to the alpha t, and you just guess that and plug it in and see what s has to be. And the reason that seems reasonable is that the first and second derivatives e to the st are just multiples of e to the st. So you plug that in. The second derivative e to the st is s squared e to the st. The first derivative is s e to the st. And then got 2 times e to the st. Put those together and you have s squared plus 3s plus 2 e to the st, where s is a constant. And that needs to be 0 for all t, which means this s squared plus 3s plus 2 must be 0. And so we just try to find the roots of that quadratic polynomial that factors as s plus 1 times s plus 2, so the roots are minus 1 and minus 2, which means that e to the minus, so if s is minus 1, e to the minus t is a solution, e to the minus 2t is a solution. Now we'll see later that the general solution is a linear combination of those two, but right now all they're doing is just finding a couple of solutions. So here's 2 different solutions. Those are the only values of s for which this is a solution. And that's all there is to the homework problems in this section. You have a couple of problems where you just have to write down the characteristic polynomial and find the roots and tell what two solutions are. Well, of course, DE Tools has a nice app for this. We're solving this equation, or you can write it as a system of two equations where v is defined to be the velocity, and then the acceleration, which is dv dt, the derivative of velocity, is minus k over m. Well, that's assuming b is 0. And you set m and k and b here. They've set m to 1, k to 2, and b to 0. That means there's no damping. And you click on some point here, like if I click on this point, that means I'm starting with a displacement of about 2 and velocity of 0, which means I just pull it back, pull it up 2 centimeters and let go of it with 0 velocity. And what happens, since there's no damping, it just vibrates forever. Doesn't die down. Now if we add a damping factor, and it draws it here as if there's a shock absorber there, so there's something that's damping the oscillation. So now the system of two equations, if you want to write it as a system, you can write it as a second order problem, single second order equation for y, or you can write it as a system of two first order equations by defining v to be dy dt, and dv dt will be minus k over my minus b over mv. So we've increased b to 1, and now let's try again. Let's start here, and now it vibrates, oscillates, but it dies down quickly. Let's try a little smaller b so it won't die down quite as quickly. Try again. And you can see it's oscillating, but the damping is causing the amplitude to die down. Okay, systems of two or more equations. It's rarely possible to solve them analytically, but in this section we'll solve a few of them. First of all, if you have two equations of this form, we'll find out in Chapter 3, we will actually get techniques for solving this special system in Chapter 3, but in general, if you have a function of x and y and t here, and x and y and t here, it's very unlikely that you can solve it. But if somebody gives you the solution, you can verify it easily enough, and that's what the first couple of problems are. They say, well, just determine if x equals 2 to the t, y equals minus e to the t are solutions, and that's straightforward. You don't know don't need to know where that came from. Just plug in x equal 2 to the e to the t and take its derivative, and x equal to e to the t and y equal to minus e to the t, and see if that's equal, and do the same thing here. And if they're both equal, then it's a solution. If it's not, then they lied to you. It's not a solution. Okay, that's a fully coupled system where the right-hand side of x prime is function of x and y and t, and the right-hand side of y prime is function of x and y. And those are pretty hard to solve, although we'll solve a few of linear problems like that in the next chapter. But if you get lucky and it's partially decoupled, that means one of the equations involves only one variable, like the second equation, if the right-hand side involves only y, then that's basically a Chapter 1 problem. At least it's a single first-order equation, and if it's separable or linear, we may be able to solve it. Otherwise, we still probably can't solve it. But this one is, well, both separable and linear, so we can solve it. Once you solve that for y, you can plug that in for y, and then you have a single equation for x. So if it's partially decoupled, you can solve the decoupled equation and then plug that in the other and solve for it. Just like solving algebraic equations. If one of your equations only involves one unknown, you solve that first and then plug that value in for the other. But this is a differential equation, same principle. But if they're fully coupled like this, then so you can't solve this for y until you know x, and you can't solve this for x until you know y, so you're kind of stuck. But if they're partially decoupled, you got a chance. If they're fully decoupled, then even better. Like this is a fully decoupled system. That just means first equation involves only x, and it could involve t also. Second equation only involves y. And so basically that's just two Chapter 1 problems, so it doesn't really even belong in this chapter. So we're going to look at partially decoupled problems where you can solve one of the equations and then plug that in the other. And you're supposed to solve this problem. That's partially decoupled. You solve the y equation first, obviously. I'm going to solve this equation. It's also partially decoupled. The second equation doesn't involve x, so that's the one you want to solve first. Obviously, if the first equation didn't involve y, you'd solve that one first. But so let's solve this with the initial condition of x equals 0, y equals 1. So here's the problem 13. We solve the second equation first because it doesn't involve x, so that's just a chapter 1 problem. And it's real easy to solve. We know y prime equals alpha y. The solution is just e to the alpha t times any constant. So we can just write down the solution. It's separable and it's linear. Either way, the solution is just arbitrary constant times e to the minus 3t. So we got y solved. Now we go plug that in for y here, and we get dx dt minus 2x equals minus 8 times y squared, but y squared would be d squared e to the minus 6t. Now you don't want to change this d squared. Normally if we have arbitrary constant square, we just say, well, that's an arbitrary constant, call it e or something. But you can't do that here because this has to be the same d as that d. So we're just going to leave that as a d squared. So now we got rid of, now that we solved for y and plugged that in here, now the first equation is just a chapter 1 problem. And in fact, it's linear, so we'll solve it using the techniques of section 1.8. It's a linear equation. The homogeneous solution is just c e to the 2t. And particular solution, what do we try? Well, the rules say if the right-hand side is e to the alpha, e to the minus 6t, you try a multiple e to the minus 6t. The fact that the constant out front involves d squared is irrelevant. It's just a constant. Minus 8d squared is just another constant. So try alpha e to the minus 6t for x. Plug that in. The x prime is minus 6 alpha e to the minus 6t minus 2 times x, which is alpha e to the minus 6t. That has to be equal to the minus 8d squared e to the minus 6t. Canceling the e to the minus 6t's, you got minus 8 alpha equals minus 8d squared. So alpha is just d squared. And so the x is then the homogeneous solution, c e to the 2t, plus the particular solution, d squared, alpha is d squared, e to the minus 6t, and y we already found. So there's our general solution. Now if we had initial conditions, we plug those in to find c and d. But remember this, you can't just call that e because it has to be d squared because it's the same d as that squared. Okay, now we're going to solve problem 36 in the review, chapter 2 review exercises, because we're going to solve this in the next section using Euler's method for systems. And I chose this because we can find the exact solution here, and we're going to use the exact solution to compare with Euler's method in the next video. But so we solve this, and again, it so happens that the second equation doesn't involve x, so that's one you have to solve first. Won't always be the second equation, just the one that doesn't involve the other variable. By the way, if this is involves y, if this is just y and that's x, that's not only not partially decoupled, that's fully coupled because you can't solve either equation until you know the other solution. But this one involves only y. Therefore, it's just a single first-order equation, which doesn't guarantee we can solve it. Of course, most first-order equations we can't solve unless they're separable or linear, but of course in the examples they usually will be. So this one is, well, it's separable and linear, so we can either solve it as a separable problem or we can solve it as a linear problem. It's easier to do it as separable probably, so you dy over y plus 1 and take the dt on the other side, integrate that, you get log of y plus 1, integrate t1 and you get t plus arbitrary constant. Now we're given initial conditions, so let's go ahead and find the constants. We could carry that along and find the constants at the end, but let's go ahead and find c now. So this says when t is 0, y is 0. So when t is 0, the right-hand side is c, the left-hand side is log of 0 plus 1, which log of 1, which is 0. So 0 equals c. So c is 0, therefore y plus 1 is just e to the t, or y is e to the t minus 1. So we got y now. Now we go back, now that we know y, plug that in here, and we get dx dt equals x times y, which is e to the t minus 1. That's separable again. Dx over x is equal to e to the t minus 1 dt. Antiderivative of dx over x is log of x. Take antiderivative e to the t minus 1, that's e to the t minus t, plus an arbitrary constant. And then we plug in the first initial condition to find d, namely when t is 0, x is 1, so log of 1 is 0, this is 1, that's 0, so 1 plus d equals 0, d is minus 1. So now solve this for x, take e of both sides, and you get x is equal to e to the t minus 1. So that's e to the quantity e to the t minus 1. And so we're able to solve that because it's partially decoupled.